Hi, and welcome to Measurement Video 1. In this video we're going to review some basic area and perimeter formulas, and we'll also have a look at some of these two-dimensional shapes, talk about the properties of these two-dimensional shapes, talk a bit about units that we use, and just get a general gist for the things that you should know prior to learning this topic. So let's go through, first of all, and just develop some of these formulas. Of course, as with any video, you can stop and start, you can make notes however you wish. So let's start with triangles. Now first we have a right-angled triangle. And in this right-angled triangle, the right angle exists here, and so the triangle has a height and a base length. The base length, of course, is that bit, and the height is the whole length of this. And you may remember that a triangle has an area formula. It's equal to half base times height. Now there's obviously a perimeter formula for triangles as well. We just need to add the height, the base, and then whatever this length here is. And you might develop that length through Pythagoras theorem or some other way, but the perimeter is just the sum of the outside. There's nothing special with perimeters and triangles. Now let's have a look at the second type of triangle, and this is a triangle of any size or shape. So we don't have a right angle in this triangle, and this next formula works in any case. It's very similar to the first formula. It's just the difference is here we have to recognise that the height is not actually one of our sides. So this time the base is along the bottom, and we have a height h, and the area is equal to a half base times height. We have the same thing, just we have to recognise the height is in a different area. Now let's have a look at some basic quadrilaterals. Remember, quadrilaterals are the grouping for four-sided shapes. So let's start with a square. Square has all sides are equal, two pairs of parallel sides, and four right angles. Now let me just denote that on here, and it's going to get a little bit messy when I'm doing this, but hopefully it won't be too bad. So there's my right angles. All sides are equal. We put a single stroke through to recognise all the equal sides. And we also have two pairs of parallel sides. So we put little arrows on to recognise parallel sides here, and double arrows to represent the other pair of parallel sides. Now, a square is nice and easy. So we say a square has side length s, or sometimes L is used, or sometimes x is used. But if it has a side length s, then it's s the whole way around the square, and the area is equal to s squared. And the perimeter, of course, is just equal to s plus s plus s plus s, which is equal to 4s, whatever s is. So that should be fairly simple for you. A rectangle has two pairs of equal sides, so this pair and this pair. We use a double stroke to recognise another pair of equal sides not equal to the first pair. And two pairs of parallel sides, so we have our double for the top and bottom here, and our single for the sides. And also four right angles. So here are my right angles again. And a square, of course, is a special type of rectangle. And so in this case we will have a side length, let's say base. And again, wherever you look up the formula, it might use different variables, different pronumerals, b, h, or x and y, or width and length. And we'll have a height here. And so the area of this rectangle is equal to base times height, or just BH. And then the perimeter is equal to base plus height plus base plus height. I've got that just from working around, and that gives me 2b plus 2h. Now let's carry on. A parallelogram next, and very similarly to that second triangle we looked at, we can develop the area and perimeter of a parallelogram. But let's start with the properties of a parallelogram. So first, a parallelogram has two pairs of equal sides, 1 and 2. Two pairs of parallel sides, parallel with that and parallel with that. Opposite angles are equal, so that means that this angle here is equal to this angle, and this angle here is equal to this angle, and adjacent angles are complementary. And that means that the circle and the triangle, when you add them together, are equal to 180 degrees. So we have lots of properties with parallelograms, and a square is a special type of rectangle, and a rectangle is a special type of parallelogram that just happens to have right angles. Now, this parallelogram, again, we say it has a base length of whatever that is, and we care a little bit about this length here, whatever s is, for our perimeter, but for our area, we care again about our perpendicular height, that height there, or this should be the same height here, or anywhere within that parallelogram. And of course the area is equal to base times height, or BH, and the perimeter is just equal to B plus S plus B plus S, which equals 2B plus 2s. Now I've used s here because I'm recognising that as not the height, but the slant height. And that'll actually be really important later on when we do some volumes with cones. So that s comes in for that particular reason. Now let's go down and have a look at the rhombus. So a rhombus has 4 equal sides, 2 pairs of parallel sides, and opposite angles are equal, much like the parallelogram, and of course the adjacent angles are complementary. So we had that circle and star add to give 180 degrees again. So a rhombus is a special type of parallelogram, and a square is a special type of rhombus as well. But rhombuses and rectangles go in different directions a little bit. So now we have some labels here, and again I'm going to try and be conventional and use this B side here, and I'll use the slant height side here, and of course I'll recognise our vertical height. Now you might not quite recognise this, but another name for a rhombus is a diamond, and if you rotate your screen around a little bit now and have a look at it, you'll see that that is a diamond. The definition of a diamond mathematically is that all 4 sides are equal and has the same properties as a rhombus. It's just the orientation is usually different in how you see it. So the area of this rhombus is base times height, or BH, and the perimeter is equal to base plus S plus B plus S, which equals 2B plus 2S again. A little bit boring because it's pretty much exactly the same as a parallelogram. Now let's have a look at a trapezium. So a trapezium only has one property, and that is one pair of parallel sides. Believe it or not, has no other properties. And I'd like to make the note here that a trapezium doesn't have to look like this one here. This is called a symmetrical trapezium. Trapeziums can look like this. This would be a right angle trapezium. Or it can look like this. As long as this side and this side are parallel, it doesn't matter where they exist. This would also be a trapezium. A bit of a funny looking trapezium, but it's a trapezium nonetheless. The nice thing about trapeziums is they're really easy to work out the area, and the perimeter is a little bit trivial again. You have to work out the length of all the sides, and so that's a bit more trivial. So the area is height. We have a base length here of B, and because we've just used B, we often call our top length A. Now, a trapezium can be cut up so that you get the triangle on this side, cut it in half and rotate that around to there, and cut this one in half and rotate it around to there, and that will give you a rectangle. So that means that the trapezium area is equal to the height times by whatever the rectangle's base length is, like a normal rectangle. And the way we work that out is that this base length, once you've moved those triangles, will be equal to the average of A and B. So the area of a trapezium is the height times by A plus B over 2. That's how we calculate an average. And of course the perimeter is equal to the sum of the sides. Whatever those values are, there's no special way to calculate the perimeter of a trapezium. So there we have it. And I might just write that out in a different form. Half H A plus B. I've just taken a half at the front, and you might see that form sometimes as well. So there's a trapezium. And here is a kite. And I just want to be very specific about a kite because my diagram does make it look a lot like a rhombus. But a kite's special in that it has 2 pairs of equal sides there and here. So the equal sides are adjacent. Now, because this looks like it's a diamond, all 4 sides are equal. So a kite is a diamond is a special type of kite. That means a rhombus is a special type of kite. So we have all these interrelated connections between quadrilaterals, and of course they're all special types of trapeziums because trapeziums only have one property, that opposite pair of parallel sides. So this is a special property of a kite. And because of this special property, it means we have these blue diagonals, and they are the important components here. And the area of a kite is equal to half times D1 times D2, where D1 is the length of this diagonal and D2 is the length of the second diagonal, and that order can be whichever way. And of course, a kite will always have side lengths that are, say, A and B, and therefore this will be B and this will be A, so our perimeter is equal to 2A plus 2B, but again, the perimeter really is just about adding up the sides, and there's no special property with kites. So we have 2 more shapes to talk about. First, a circle, leading a little bit to a semicircle, and then a sector, which is just part of a circle subtended by a certain angle. We'll talk a bit more about that in a second. Now let's start with our circle. A circle obviously is defined by the points that are equidistant from a given central point. So let's call that C, that central point. And everywhere on the outside of the circle is R away from C, where R is equal to the radius. Now I know that sounds a little bit technical, but as you move forward mathematically, you're going to have to start thinking about things like that and how a circle works. But anyway, you might remember the area of a circle is equal to pi r squared. And you might remember that the perimeter, which we often call the circumference, is equal to 2 pi r, or pi times d, where d is the diameter. And so remember your work with circles, you have radiuses, that's half the diameter. Diameter goes straight across the circle through the centre, and of course perimeter is equal to the circumference. Now, if we're talking about the sector of a circle, this is one part of the circle, and it's subtending a given angle. So what that means is it's got a given angle on the inside. So I'm going to label this angle here by traditional angle label theta. And so this circle has the same circumference and perimeter and area of a normal circle. So as usual, we have a radius, which I'll put down here, and the area is equal to pi r squared, and the circumference is equal to 2 pi r. But you'll see I've left a little bit of a gap, because we don't have a full circle. We have the proportion of a circle, so not a complete circle, part of a circle. So now, the area is actually equal to theta over 360. So that's how much of the circle is there. So for example, if there was 90 degrees, well, that would be a quarter circle. So it would be 90 over 360, which simplifies down to a quarter. And of course, the circumference is theta over 360. And this is sometimes also called this funny sort of italics L, which is the arc length. And so I'll put a label over here. The arc length is this bit here. And that's calculated by theta over 360 times by the circumference 2 pi r. And so really I should cross this out and put arc length there. But I'm just leading you in, obviously. But in this case, we have to be very careful because the perimeter is actually equal to the arc length plus 2 times the radius. This radius and this radius, because the perimeter is the whole way around the shape. So the perimeter is theta over 360 times 2 pi r plus 2r. Now you can factorise that and you can do things like that. You can simplify the 2 into 360, but I'm going to leave it in this form because I think it's really important you recognise that sometimes you might already know the circumference. So you won't be substituting in 2 pi r, you'll be substituting in a known number. And there's different little things that can happen with examples that you do, so it's often better to think about the big picture here. So there we have it. All of the common areas and perimeters that you'll need to know. And of course, just as a quick side note, let's talk about units. Obviously, perimeter is a length, so it is one-dimensional, 1D. So a perimeter could be measured as millimeters, centimeters, meters, kilometers, as well as all those other non-metric measures such as miles or feet, plus many other different types of measures, but essentially it's one-dimensional. The area, on the other hand, is an area, and so it is two-dimensional. You multiply one dimension by another, which means it will be measured as millimeters squared, or centimeters squared, or meters squared, or kilometers squared, or even miles squared, etc. Feet squared, cubits squared, there's heaps of different measures out there. So there's some units.